Hello everyone, welcome for the quantum space-time seminar. Today we are very happy to have Sebastian Mizera from the institute, and he's going to tell us about crossing symmetry in the planar limit. Over to you, Sebastian.
Okay, awesome. Thank you, first of all, so much for the invitation. I really wish I could be there in person, but maybe at some point in the future. Let me also point out that it's currently 11:30 p.m. Where I'm now. So it's actually going to be the first seminar that I'm going to start on Sunday and finish it on Monday, and hopefully not the last. Okay, so today I wanted to start. Let me just minimize this. Okay. Today, I wanted to start with a historical remark that this year in 2021, we're actually celebrating 80th anniversary of the appearance of one of the very first Feynman diagrams. This is how it looked like, and it appeared in this old paper of Stuckelberg in 1941. However, for us today, this is not even the most exciting part of this paper. In the very same work, he made a revolutionary at the time observation that particles are indistinguishable from antiparticles with the opposite energy and momentum, at least classically. Okay, so at the level of observables in quantum field theory, this statement translates to the property called crossing symmetry for the full S matrix. Every time I say S matrix in the talk, what I mean is that we have to impose the on-shell conditions and the momentum conservation. And this statement translates to basically observation of the incoming particle and an outgoing antiparticle. And to perform this observation, you measure this process with an arbitrary number and arbitrary type of the other states. Okay, and then at this level, the question of crossing symmetry translates to the question whether the two scattering processes, this one and this one, can be related by analytic continuation of one to the other. Let me at this stage maybe emphasize that sometimes people use the term crossing symmetry to really mean permutation invariance, meaning that you can exchange particles and get the same function. And this is not what I will be talking about today. I will be just talking about taking a single particle and a single antiparticle, the two processes, and trying to devise an analytic continuation between the two. So that famously has been an open problem since its introduction by Gell-Mann and collaborators in the 50s. I think nowadays it is widely believed that this property is actually true, but as we'll see, that crossing symmetry has almost no theoretical evidence to support it. Okay, so yes.
So in the beginning, you distinguish between the permutation invariance, which is sometimes called crossing symmetry, and the notion that you are saying, talking about here. But
yes.
Aren't they related in some way?
No, they're completely orthogonal. So we could have crossing symmetry without permutation invariance. For example, when you have S matrix with all the distinct states, and likewise, we can have permutation invariance without crossing symmetry. For example, in the examples that I will mention, for example, in 2 dimensions. So they're really distinct. This statement here is really, we can make it for any type of the particle that we exchange from particle to antiparticle. They don't have to be, it doesn't have to be permutation invariant with respect to the other particles.
Yeah, but there is a, okay. Yeah, thanks.
Okay. So I should say, please feel free to interrupt me at any stage. So the plan for the talk is as follows. First of all,
Sebastian, sorry, since you're pausing, please allow me to ask this, but then just postpone it, which is there a connection between CPT invariance and crossing symmetry? I mean, is this something you'll come to, probably, or not at all? Okay, just for you to.
Yes, so the distinction that I will make is that CPT invariance is a kinematic statement, that the states are related in some way, which I will see, as we will see, it translates to sort of statement at the level of Feynman diagrams. Feynman diagrams with a particle and an antiparticles are like complex conjugates of each other, or with the appropriate identification. And this is distinct from this statement, which is a dynamical statement. Whether on the level of the S matrix, we can perform analytic continuation in command understanding environment. But I'll come back to this.
Thank you.
Please feel free to interrupt me if Okay, so first of all, I will have to explain basically why do we have to ask this question in the first place. Of course, people have attempted to answer it in the past. So first of all, I have to explain why the previous approaches failed in answering this, basically. Then I will propose a new strategy in perturbation theory, more strictly speaking in the word-like formalism. Then what we'll do is we'll identify possible obstructions that could prevent crossing symmetry from being true. And then finally, we'll not be able to prove it in the full generality, but what we'll be able to do is prove it in the case of planar limit in perturbation theory. Okay, so first of all, why have the previous approaches failed? Well, it all boils down to the sort of unfinished business in the S-matrix theory, which is the following question: whether what analytic properties of the S-matrix guarantee that it corresponds to a causal scattering process in space-time? And we still don't have a general answer to this question. We, of course, we know about a lot of necessary conditions. They're usually related to things like Shapiro time delays that you can test if that your amplitude can be causal if it has a Shapiro time delay, but we don't know about sufficient conditions.
Sorry, Sebastian, could you say what has it been? Perhaps this is what you meant, but what do you mean for an amplitude for an S matrix to be causal?
That's a very good question. There's actually many different definitions of what causality means. One of them is sort of absence of Shapiro time advances. Another is microcausality. There's a thing called Bogolyubov causality conditions. There's different notions. It's actually not clear which one of them is the best notion that we want to have. But it's true that in none of them we have sort of an equation or a condition on the S matrix that automatically tells us that if that condition is satisfied, that the amplitude is causal or it corresponds to causal process. That's in contrast with, for example, unitarity, where we can just take the amplitude, we can mod square it. If it's equal to 1, it's unitary, otherwise it's not.
Sorry, and you mentioned 2 or 3 different notions of causality.
Yeah.
Do any or all of them completely capture the intuitive notion of causality as a necessary and sufficient condition, forgetting about what equation they impose at the moment?
Sure. I mean, if by intuitive, we'll come back to the notion of microcausality, which is the one that commutators of local operators vanish at space-like separations. I guess that's the most intuitive to most physicists.
That's great, but it doesn't. But since it's talking about off-shell correlators, it's not directly about an S.
Yeah, as we'll see, in fact, on the next slide, that's exactly the point that I wanted to emphasize, that the previous attempts at proving crossing symmetry, or more generally studying causality relations for scattering amplitudes, basically failed because of, within the LSD formalism, the notions of on-shell S matrix and space-time causality are sort of incompatible with each other. So I will.
Please go on. Please go. Thank you.
I will explain this in more detail. Let me just emphasize that I think this is a sign that we need a better formulation, sort of intrinsic formulation, rather than LSZ. And of course, there's a lot of work on the extracting flat space S matrices from IDS CFT with a long literature. And just let me mention that there's also great work, great recent work coming from TIFR in this specific direction. So let me first explain what I mean about this incompatibility of the on-shell S matrix and space-time causality on a simple toy model. Okay, so let's say you have a causal signal. So causal signal, it means that something caused it at time t equals 0, and then that signal later propagates to infinity. And let's say now we want to make Fourier transform the signal to the energy space. Okay, so energy space, we just do this Fourier transform, and the signature of causality is the fact that we integrate from 0 to infinity as opposed to minus infinity to infinity. Okay, and then you can see that at this level, this integral here on the right-hand side only exists when the imaginary part of the energy is strictly positive, because this is precisely what guarantees the exponential suppression of this integral at infinity, at least for polynomially bounded f's. Okay. So, and now what we see is that this notion of just convergence of this integral is directly incompatible with dispersion relations. And this is something that plays a toy model, is a toy version of the on-shell conditions, basically imposing that the energy is equal to energy squared is equal to frequency squared, which has to be always greater or equal to 0. And let's see what this tells us. Okay, so first of all, we know that this equation tells us that the imaginary part of E squared is equal to this, and it has to be 0. But the Fourier transform only exists when this is strictly positive, and that basically forces the real part of the energy to be strictly 0. Now, the real part of this equation tells us that we have 0 minus something strictly positive. So that tells us that the real part of the energy squared has to be strictly negative, which is in direct contradiction with this condition. Okay, and this tells us that basically this notion of causality basically converges of this integral, and the on-shell conditions they're directly orthogonal to each other. So this means that we are essentially forced to first define the physical, first define the unphysical Fourier transform, unphysical observable in the energy space, and then approach the physical value by analytic continuation. And of course, in this case, this is very simple because we just can approach the real values of the energies from the upper half plane. Okay, so in this case, actually, it turns out that the analytic continuation is a simple limit in which we just go from upper half plane to the real axis. Okay, as we'll see, this drastically changes in QFT, as you might expect. So first of all, in QFT, what we have to use is we use the notion of microcausality, which, as we mentioned before, is the statement that commutators vanish at space-like separations. Of course, that notion of microcausality is directly related also to locality, just the fact that there exist local operators to begin with. And also, one other thing that you need for those arguments to work is unitarity, although I will not have time to explain it. Okay, now what happens is that the problems becomes extremely more severe. So if you go through this analysis, you would find that this is sort of the typical LSZ reduction formula, in which we first have some integral to do, and basically using very similar arguments to what we've seen on the previous slides, we can show that this does not exist on shell, meaning it does not exist when the mass of the particle is real. And then what we have to do later on is we have to perform an analytic continuation to get the S matrix. And in contrast with what you might read in the books, this is actually not a limit, it's an analytic continuation. The difference is that, or essentially what you have to do is that all the physics has to be understood by a supposed analytic continuation across the light cone. So we have some light cone configurations, which are off-shell or imaginary mass, in which these notions of causality and LSZ reduction are really well defined. And then what you have to do is you have to perform the analytic continuation to physical masses. Okay, and actually, it's not even clear that such an analytic continuation exists at all. If it exists, whether it's unique, does it always give you the same answer? And if it does exist or if it doesn't exist, what is the physical explanation one way or another? Yes.
So is it better to consider massless particles from this point of view? Because
no, it actually works.
Because then it is a limit, right? Then isn't it a limit? You just approach the light cone.
Yeah, it's actually worse for from this point of view of just analyzing the convergence conditions. It's the same. I mean, we have a greater or equal here, so it does not exist even in the massless limit. But LSZ reduction itself is not really well defined for massless big particles to begin with because of the infrared issues.
Yeah.
So those sort of things. Really.
Yeah.
So as we'll see, basically the progress in the last century in doing this analytic continuation has been fully confined to massive particles.
Sebastian, please don't slow yourself down. I'm sorry, I don't have a good understanding of all this, but when we calculate for some standard field theory in the classroom, the S matrix through the LSE formula, we don't really do such an analytic continuation or whatever, right? But are you saying it's actually built into the formulas? I haven't quite thought about it in this way. That's why I'm asking you.
So what we
yeah, go ahead.
In the classroom, we almost never, pretty much, we never start with the space-time correlator and then do a Fourier transform. Instead, what we do is we use Feynman rules.
Yeah.
At the level of Feynman rules, for example, at tree level, it's completely obvious that the function is just meromorphic function, so you can continue it wherever you want. Yeah. At loop level, we have branch cuts, and at that stage, it's not entirely clear, like, you have to continue it to avoid branch cuts and so on. Mm-hmm. And from examples, at one loop and two loops, you can do it, but we don't know the general non-perturbative prescription to actually doing it.
I see. Okay, thank you.
And just to make sure, Sebastian, you're saying that the subtlety here lies in that if we took the space-time amplitude and then try to Fourier transform it directly on shell, there would be a subtlety there. Right? That would not be well defined.
Yes, it just cannot be done on shell. That's the whole issue, and the whole reason why people had to write long papers explaining how to do apply some theorems in complex analysis to actually improving the situation.
Right.
Thank you. Sorry, but going back to Sandeep's question, in Feynman rules, there is some tacit prescription given, or is it that even doing these integrals I should encounter ambiguities?
We'll come back to Feynman rules and we'll study very carefully what has to be done to perform analytic continuation.
Yeah. Thanks.
But for now, you're welcome. So for now, let me emphasize, sorry,
just again about the same set of questions. See, you're saying that what's not clear is that if you just naively evaluate the Feynman diagram on shell, that's the same as evaluating it in some place where it is the Fourier transform of the position space and then analytically continuing.
Sorry, I wanted to, at this stage, I'm working fully I'm looking for a non-perturbative statement. And later on, and that's certainly the way that people have been trying to approach this problem in the past. Later on, I will move to, strictly speaking, perturbation theory, and then we'll see simplifications that arise.
Thank you.
Okay. So the review of the results that basically happened in the last century. So this is mostly due to work of Ross, Epstein, and Glasser between 60s and the 80s. What you have to do is you have to exclude the massless particles. So assume that you're working with a QFT with a mass gap. You also have to forget about higher point processes and focus mostly on 4-point scattering. And then also you have to forget about the notion of crossing of a single particle. And instead, what we can ask is about crossing between different scattering channels. Okay, so one of the very concrete results that has been proven in these works is that if we look at the Mandelstam invariants S and T, and then we fix T to be negative, so the physical momentum transfer, and then if we look in the upper half plane in the S variables, then what has been proven is that there exists some neighborhood of the physical regions, some are here and some are here, as well as some neighborhood of the infinity, so some are here, where you can prove the amplitude does not have any singularities and it's fully analytic. And everywhere else, in principle, non-perturbatively, there could exist singularities. Okay, and what this allows you to do is start with the sort of S-channel scattering matrix, somewhere here, and perform analytic continuation, sort of going here to asymptotically large energies, so beyond the Planck scale, and then going around in the upper plane, and then approaching the U channel from the unphysical side. Okay, so this is basically the most advanced results that we know about analytic continuation of non-perturbative S matrices at 4-point. Let me also mention that what you might be used to is seeing the so-called Euclidean region that people often use to perform analytic continuation. However, the Euclidean region doesn't exist for generic S matrix, and this is basically the reason why it couldn't have been used in the past.
Sebastian, one question. So the structure of singularities that would have prevented me from doing the analytic continuation through this gray region is if the singularities were accumulated and formed a barrier, right? If there is a one or two singularity, I can just get past. Isn't that true?
Yes, if there was a pole, you can just go around it. The more possibility is that there could be some branch point with a branch cut extending through it. So, for example, if there's a branch point with a branch cut here, then of course you cannot. I mean, you can continue through the branch cut, but you would not get the physical result. So you have to go around it.
So you will end up on a different sheet.
Exactly. Yeah.
Sorry, Sebastian. I sometimes hear people saying that it is either believed or known that on the principal sheet of the S matrix there are no singularities apart from those dictated by unitarity. But you're saying that's not true.
That's only true in a very special case, and that special case is if you scatter the lightest state in a theory with a mass gap. That then and it's essentially boils down to the existence of this Euclidean region in such situations, and that's exactly what has been studied in the past. If you have a mass gap theory and you have scattered the lightest state, it means that you can show that the only singularities are starting at the 4m squared at the real axis, and everywhere in the upper half plane and lower half plane there's analyticity. But that does not hold in general. In particular, for example, if you include massless particles, the gap closes. And this is precisely where you might see a chance of some singularities in the upper plane.
Thank you.
So
could you say what this Euclidean region is?
Sorry, what was the question?
What is this Euclidean region?
If you haven't seen it, then don't worry. The so-called Euclidean region is precisely it's some region close to the origin of the kinematic space for small s and small t, where the amplitude is real and non-singular, and it exists under some kinematic conditions on the S matrix, but not in general.
And it does not exist for massless scattering.
It does not exist for massless scattering. It closes to a point.
And so one more question, but maybe it's not related, but just to kind of get oriented for the future discussion. I don't know if it would be needed, but if you think in terms of STU and momentum conservation, then what is the space of STUs? Do you know?
So
without imposing on-shell condition.
Sorry, I should have mentioned the S plus T plus U is equal to 4m squared, or sum of the masses squared.
I see. So all of them. Okay.
Not independent of each other. So the only independent variables in the game are S and T in this case. For the S matrix. If you wanted to do off-shell correlation functions, you would also have U, which in principle could be independent. But today we're talking about observables, in which case we only have S and T. Sorry, I should have mentioned that. So let me maybe to make some more tangible connection with recent work on low energy effective field theories. So this is essentially work following the paper of Adams et al. In the 2006, which recently has become generalized to more and more cases. There, what you need to do is essentially compute integrals over such contours here in red. And those integrals, what they do is they give you some kind of sum rules for relating EFT coefficients in the IR to some physics in the UV. And in order to make such constraints on the Wilson coefficients in the IR, what you need to do is you need to perform this integral here, and you need to assume that there's no singularities in this region between IR and UV. And this is, of course, far beyond what has been proven non-perturbatively to exist. In principle, there could be singularities, or it's not known. The extent to which they could be there is not known. So basically, validity of these EFT constraints from recent papers essentially hinges on the analyticity assumptions that we put on the S matrix. And as far as I understand, there's no sort of physical intuition why those assumptions should be there. It's more or less just simplification. Okay, so this whole program leaves us with many unanswered questions. Many of them have been brought out by the audience. First of all, can we identify what kind of singularities are absent in these asymptotic regions and why? What is the physical reason? Then whether the connection to asymptotic kinematics in the first place is accidental, or maybe we can make some statements about analytic S matrix at finite energies. Then can we separate the assumptions of causality from those of locality, which is something that we know we have to do for the quantum gravity in the long run. Then, of course, can we generalize these 4-point statements to higher multiplicity? Can we include massless particles and so on? And finally, the big question, can we realize the dream of Stuckelberg and collaborators in which we can continue a single particle into a single antiparticle? Okay, so clearly a new strategy is needed. Maybe let me pause briefly in case there's any question about this.
So the question of whether there exist singularities on the principal sheet within perturbation theory is more known than non-perturbatively.
So in this talk we'll see the sort of the most advanced constraints that exist to date.
Thank you.
So Sebastian, one question.
Yeah.
Please.
Sorry, just
So,
sorry. So if you consider 2 to 2 scattering and take one of the particles to its antiparticle, so that becomes a decay process, right? So if such a hello, can you hear me?
Sorry, you said it becomes a what process?
A decay.
Oh yes, decay. Yes, sure.
So then if it is not allowed on shell, right? The masses are not compatible. Then this will not happen. So you should get 0, right? So
yes. So we'll actually. This is a special case in which you have just. I'll come back to that. But essentially, we try to avoid situations in which we leave out one particle on in state or one on the out state.
I was going to ask. So is the question? Can the question be that 0 is an 0? Would it be an analytic continuation of some function, or in this context, how should I think of this?
No. In this case, you should just think of the kinematic region in which the decay process exists to just be not a region that doesn't exist. So that question just doesn't make sense.
Yeah. Okay. Thanks.
Sorry, there was another question or comment from.
I was commenting that in perturbation theory, I think these Landau singularities people expect to be there on the principal seat, coming from the solving Landau equations for each Feynman diagrams, and people expect that at least those will be there in the off-shell Green's functions and eventually in the analytic continuation.
Yes, you're absolutely right. So what we'll see is that the whole trouble will be in constraining the places where anomalous thresholds, as you mentioned, cannot exist. So we'll come back to that and we'll study them in more details very soon.
I see. And another thing you said that you do not know whether this analytic continuation is actually multi-valued or single-valued like that. But as long as I understand that the derivation of pre-domain, the off-shell formulation from microcausality and all, so that primitive domain is simply connected. And as long as the analytic continuation is simply connected, I do not know how this Bro-Sefton and Glaser region ultimately that was simply connected or not. But if we know that the analytic continuation is also simply connected, then the answer could not be multi-valued, right? I mean, in a simply connected region, the analytic extension is always single-valued. I think so.
Yes, absolutely. So in the cases that it has been the primitive region of analyticity that you mentioned is the one that exists purely off-shell, so it has no overlap with the on-shell.
That do not contain any on-shell points, so you have to continue and then evaluate oneself.
Yes, exactly. And that has been essentially the content of the result that I mentioned on a cartoon level a couple of slides ago, basically leading us to those constraints at 4 point.
Okay, but do you think those continuations will be could be multi-valued or something from the primitive region domain?
It's not known more generally if they extend beyond those cases. So we don't know. Okay, so clearly a new strategy is needed, and what we'll do in this talk is we'll reconsider this problem as everyone was already hinting at in perturbation theory, basically coming back to where it all started, and more specifically we'll be working in the word-line formalism. Okay, so a couple of simplifications that I should first say that even though we'll go to perturbation theory, we'll still try to make statements which are valid to all loop orders at any multiplicity for all spins and masses. So we'll still retain a large level of generality. And one of the advantages of using perturbation theory is that we can separate the questions about analyticity of the S matrix from those of UV and IR divergences, which is something that we cannot do in non-perturbatively. In perturbation theory, we can still simply use DIMREG and ask those questions in DIMREG for any theory, even if it has UV and IR divergences. And everything that I will say in the following slides will be valid in any theory in larger than 2 dimensions that satisfies CPT invariance. What CPT invariance means for the purposes of this talk is that Feynman rules will be crossing symmetric, but that by itself does not imply that the Feynman integrals are also crossing symmetric, and that's in fact going to be the whole content of what we are trying to show. So there's a question?
No, thank you. This was part of my confusion. Okay, thank you.
Okay. So let me actually emphasize, since this has some bearing on the work done in this group, that in principle the Chern-Simons S matrices will be excluded from the analysis precisely because of the CPT. They have the additional anionic phases when we exchange particles. So that by itself does not mean that the crossing symmetry does not hold. It simply means that you have to modify what do you mean by crossing symmetry, basically into first perform the analytic continuation, and then in addition to that, multiply the S matrix by some additional phases, as explained very beautifully in this set of works by Shiraz and collaborators. Okay, let me also mention that two-dimensional S matrices give simple counterexamples to crossing symmetry. And that's essentially, the reason for that is that integrability in 2 dimensions implies no particle production. And in particular, what this means, for example, at 6 point, that the scattering of 3 to 3 particles is non-trivial, but scattering of 2 to 4 particles is trivial, gives you 0 identity. And because it gives you 0, there does not exist a holomorphic function which is 0 in some region and non-zero in other ones, and that automatically tells you that you cannot perform analytic continuation from this process to this process, at least not if you use a single analytic function, which is the S matrix. In principle, you would have to split it up into multiple analytic functions. Okay, and the reason why this fails in 2 dimensions is essentially that because of the 2 constraint kinematics. So basically, Mandelstam invariants are no longer independent of each other, and that's basically means that the kinematic space collapses because of these additional constraints coming from space-time dimension. And let me point out that a similar situation happens for scattering of more than 5 particles in 4 dimensions. And this is exactly where you might get worried that perhaps some similar mechanism would prevent crossing symmetry to hold even in 4 dimensions. Okay, and let me also mention that it is known that the non-perturbative results actually fully carry over to perturbation theory. And this is explained in the beautiful work of Ashok Sen and collaborators in the context of string perturbation theory, in which they also showed that the locality assumption is essentially not needed if you confine yourself to perturbation theory. This, of course, still leaves us with the questions of massless particles and the higher multiplicity and continuation of a single particle and so on. Okay. So for the purposes of this talk, the simplification coming from perturbation theory will be that the studying of singularities of the S matrix can be mapped to a study of the wordline saddle points in the wordline formalism. And the reason why this is significant is that the question about singularities, which used to be question about analyticity, now translates to a fully algebraic problem, simply because we have well-defined equations for the saddle points of the action. Okay, so let me now get slightly more technical. So contribution from a single wordline Feynman diagram looks as follows. So first of all, once you localize there's a free action that you put on the wordline. Once you localize the free field, you're left with the so-called Schwinger parameters. Okay, so these are the only dynamical variables in the game. Okay, so I'll call them alpha sub e, where e ranges from 1 to capital E, which is the total number of edges in your diagram. Okay, then in here we also have some Laplacian raised to power of the dimension here. Also some perhaps interesting polynomial numerator that encodes all the contractions of the OPEs of the wordline and depends on the specific matter content that you put in. But for our purposes, the most important part will be the rest of the integrand here with the V, which is what I call the wordline action. And at this stage, you can show that the Feynman I epsilon prescription, or equivalently convergence of this integral at infinity, it can be imposed by imposing that the imaginary part of the action is strictly positive. And in contrast with the non-perturbative avatar of what we've seen before, this imaginary part of V being positive is exactly the physical condition that we want. It selects the correct branch of the scattering amplitude. Okay, so now to those of you familiar with string theory, you would know very well how the wordline action looks like, because it's very similar to the string action. It's simply given by a double sum of the external vertex operators, which carry the momenta pi, and we dot it with in pairs pi.bj, and then we weight it with the Green's function on the wordline. Okay, like so. And there's also this mass contribution from the mass of each individual segment of the wordline. Okay. So at this stage, Green's functions have to be treated not as in terms of positions of the vertex operators, but instead as functions of the Schwinger parameters, the alphas. Okay, so for example, locally they behave as this, where the positions of the vertex operators are tau. Then locally it behaves linearly, and it also tells you that once you promote this to a holomorphic function of Schwinger parameters, it has to linearly depend on the length of the edge E, stretching between pairs of vertex operators. Okay.
Just a quick question, just to understand, like, are there also loop integrals or like loop momenta and so on in V, or are those not?
So this is equivalent to doing loop integration. In fact, you can show that this integral, you can just massage it with different identities, and you can show that this is exactly the thing that you would get from doing loop integration.
I see. Okay, got it. Thank you.
If I had more time, I would explain it, but I thought it would be more intuitive.
Sure. Got it. Thank you.
Sorry, Sebastian, these PIs are external momenta, or?
Yeah, so yeah, PIs are the external momenta coming from attaching external particles to the wordline.
But Gij are defined with Ij being any points. So Ij,
yeah, you can compute Gij between any pair of points, but the combination that appears in the action is only between points where the external momenta are attached.
So I don't understand. So wait, sir. I mean, the way you explain GIJ is the length of this interval, right, between these 2 points.
Sorry. This is the GIJ only locally behaves as this.
Okay.
So,
when they're close to each other. Okay.
Exactly. Otherwise, it's a more complicated expression, and I will show later on some examples of the action in case this was a bit confusing.
And the P's are on-shell momenta, but otherwise complex.
Yes, exactly. Yeah. And M sub E would be mass of each propagator or each edge. Okay, please let me know if the notation needs further explanation. But in the meantime, let me mention that the singularities of these integrals appear precisely in the classical limit as you take h bar going to 0. And you can, as you can see from this form, this is exactly where you see saddle point analysis. Okay, so first of all, there's two classes of the saddle points. There is this bulk saddle points that correspond to varying the action with respect to all the Schrödinger parameters, as usual. And also there's boundary saddle points, which happen when you're at the boundary of integration, when a subset of Schrödinger parameters degenerates to 0. And as foreshadowed before, these are actually equivalent to so-called Landau equations, which impose the condition that all the internal propagators go on shell. Okay, so you can equivalently think about singularities as the saddle points or as solutions to these on-shell conditions for all the internal edges. Okay.
Sorry, I'm sorry to constantly interrupt, but just an ill-formed question. There's another process in which we put internal propagators on shell, and that's when we try to study unitarity. So there seems some sort of connection between these Landau equations and what we get from unitarity, and I wanted to understand how tight that connection was.
Yes, so the unitarity is specifically for the processes in which we have sort of left amplitude, right amplitude, and then you have many lines between them, and you put those lines on shell. And that's actually a special case of more general class of singularities, and that is what we call a normal threshold. The ones where you have just particles exchanging from left to right. But in general, there could be more complicated singularities, for example, when you exchange particles in a triangle. And these are the anomalous thresholds.
Thank you.
They are still consistent with unitarity, but it's not as obvious to see as the normal thresholds.
Thank you.
Okay. So then the wordline action, what distinguishes wordline action from, say, string action or any other type of the action is that it is actually homogeneous under dilations. Okay, so if we rescale all the Schrödinger parameters with some overall scale, then this action actually picks up an overall number, but otherwise doesn't change. Okay, and this has three important consequences. First of all, the action vanishes on the saddle points. So this is simply because if it's a homogeneous function, we can apply this dilation operator to the action and we get it back here. But on the saddle point, all the derivatives vanish, and that automatically tells us that the action has to vanish as well. Now what we can do is we can take this overall scale lambda and we can just simply integrate it out. Okay. If you work out how this looks like, you will find that there's this number gamma could be degree of the graph. And when we just do this integral over the overall scale, we find that it behaves like 1/v to this power. And that's precisely why the saddle points in this case are related to singularities, because we have 1/0, at least when the degree of divergence is positive. Okay, and then finally, what we have is we have E equations, where E was the number of Schrödinger parameters. That's because we just have saddle point equations. But the Schrödinger parameters are only defined up to the overall scale. So there's actually only E-1 independent numbers. And this tells us that we have one-to-many constraints. And that one-to-many constraints has to be imposed on the external kinematics. Okay, so for instance, if we study 4-point scattering, we have the independent Mandelstam invariants S and T. So for example, we can look at what happens in the ST plane, like so. And in this ST plane, we usually have some physical regions, the ones that are shaded here. For example, this is the S channel, this is the T, and this is the U channel. And what the way that those saddle points look like is that at the generic point in the space, we have no singularities. This means that the amplitude is just well defined. But in principle, there could be singularities in some codimension 1 places as some special values of the kinematic parameters. Okay. The simplest example is when S is equal to 4m squared. So it would be a line like this.
Yeah, and just to make sure I'm the one too many is one real too many conditions, right?
One complex.
Oh, then I don't understand. If it was one complex condition you're imposing on, oh, I see. Because you've got S and T both complex, and then you put one more complex condition.
Yes, exactly.
Thank you.
We have, just to reiterate, in this case, we would have ST, so this would be C2, and then we put one complex condition, so there's codimension 1 singularities. Okay.
Thank you.
Thank you. So then I should speed up. Then these singularities are known as the anomalous threshold.
Sebastian, just to tell you that you'll get exhausted at some point, but we are very casual about time, so you should go ahead as long as you like.
Okay, that's great to hear. I don't need to sleep today. Okay, so these singularities are known in the literature as the anomalous thresholds, or in the special case, as I mentioned before, when they're aligned in one dimension, they're called normal thresholds. And these are intrinsically Lorentzian phenomena. So, for example, they don't exist for Euclidean scattering, and at least partially they encode causality conditions in perturbation theory. If nothing else, they tell you where singularities of the S matrix could be. So they constrain somehow the analyticity of the S matrix in the complex and in the real domain. So let me start with a simple example. Okay, this is basically this is just the triangle integral. It has four external legs. And let's say it depends on the kinematic invariant S, which is a momentum going in this direction. Okay, and then you can evaluate the action, and in this case, it's simply equal to this function. Okay, where S is the Mandelstam invariant, M in this case are external masses, which I take all of them for simplicity to be equal, and lowercase m are the internal masses. Okay, so this I just wanted to flash it to you just to show you that it's nothing complicated. It's just a rational function. Okay, then what you do is you have to vary this rational function to find saddle points. And in this case, you actually find there's a single bulk saddle, and as we said before, it puts one constraint. It's some specific value of Schrödinger parameters, but also it puts one constraint on the S Mandelstam invariant, and it tells you that if you solve it, the S has to be equal to this.
Hi.
Yes.
Question. Yeah, so these things you have evaluated some Feynman diagram in Schrödinger parameterization and solve the linear Landau equations and put them on shell. You have evaluated this and got this new, right? Am I right?
So this is the wordline action, which depends.
The integral you show that time that corresponds to some Feynman diagram, loop level Feynman diagram. Am I?
That's correct.
Okay, so these are evaluated on shell. These new are evaluated on shell here in this slide. So, so local theory and non-local theory, like string field theory, those will correspond same new, right? I mean, in this 2-to-2 scattering level, will be any change here for non-local theory in this new or something? Because
there's a couple of ways of thinking about it. One is in string field theory, for example, you can sum over infinitely many diagrams. And in this case, for each diagram, you would have one of these. Another way of thinking about it, and
suppose in string field theory also, like you said that D. Lacroix, Arvin, and Singh work. So they look at every Feynman diagram, but on off shell. Suppose I do your thing directly to prove crossing symmetry, and you have probably evaluated each diagram and take any string field theory diagram for 2-to-2 scattering and evaluate same integral you will get, right, corresponding to that Feynman diagram. So is there will be any change in the new for non-local theory?
I was just going to mention that I think there's a work of Tamboulis, if I'm not mistaken, who shows directly how to translate non-local vertices in the loop momentum space to the basically this.
Okay.
You just get a more complicated function of Schrödinger parameters. It's still a function of Schrödinger parameters, but something more smeared, sort of. But I have not analyzed this.
Okay.
Sorry, and Sebastian, I think you've said this and I missed it, but did you explain to us why saddle points of your action were the potential non-analyticities?
So it basically comes from here. It tells us that the saddle points are singularities, and then the potential types of singularities that could appear are, they could be at tree level, they could be poles, but other types of singularities that can appear, you can analyze it essentially as a consequence of this, are branch cuts, and they could be either logarithmic or square root branch cuts.
Sorry, and you can show that apart from saddle points, there are no other possible singularities. Yeah. Thank you.
Sorry, there's something called second type singularities, but I didn't want. They're basically collinearities. So there's these and basically collinearities. So collinearity would be here, this curve.
Okay, thank you.
Okay. Let me maybe in case, yeah, the lines that I drew here, the singularities are the non-analyticities. So this is what we want to avoid in principle if we do analytic continuation. Okay, so in this case we also had the we also have the boundary saddle. Okay, and the boundary saddle in this case comes from the place when the boundary in the Schrödinger parameter space in which alpha free goes to 0. And this is precisely the normal threshold because it corresponds to this propagator becoming very short, and then we still put the other propagators on shell, and this gives rise to the famous S equals to 4m squared. Okay. Now what happens in this simple example is actually very interesting. When you consider the mass of the external particles, capital M, to be larger than 2 internal mass. And what you can show is that there's the normal threshold here at this position that we determined on the previous slide. And there's also the anomalous threshold here. And then if we study what happens to the branch cuts extending from those branch points, we see that there's actually a branch cut extending from -infinity to this point, from this to the normal threshold, and from the normal to +infinity. What this actually tells you is that we are dealing with a function which is defined, completely well defined in the upper half plane, completely well defined in the lower half plane, but you cannot continue between our upper and lower. Then naively, you might think that this could be a contradiction with, crossing symmetry. But what saves the day is that the S channel, the physical way of approaching the S channel is from above in case of this diagram. And then for the U channel, it's actually with, from above in the S plane, but from below in the U plane. Okay, basically because of momentum conservation, the imaginary parts of U and S have to add up to 0. Okay, so here we have to approach it from above. Okay, so in this case, the S matrix, you can simply continue it from here to here, and you never have to cross to the lower plane, even though the amplitude would be discontinuous there. So it's not in itself, it's not a contradiction, but it's something that might worry you. That, well, what happens if such such branch cut structure becomes more severe and it prevents some kind of possible analytic continuation.
Sorry, capital M was the mass of the internal particle?
The capital M is external.
External, I see, and internal is little m. Okay, so precisely in this situation, when we start summing Feynman diagrams, the external particle will not really be I will get an imaginary part, will not really be a good external state, right? Because it could decay.
Sure, yes.
So is, of course, for any given Feynman diagram, you don't see this, but would that sort of self-consistently play into the picture?
Yeah, I don't know exactly how to take that into account. For now, what we confine ourselves to doing is just doing things diagram by diagram.
Okay, thank you.
But let me also one of your previous questions was about this Euclidean region, and that was, I mentioned, discovering of the lightest state. Of course, this does not happen when you have the lightest state because m would be equal to m, and that doesn't happen here. Okay.
Sebastian,
awesome.
one question.
Yep.
So, just from the analysis of the action and the saddle points, how do you determine the type of singularity and the structure of the branch cuts, or is that a more involved analysis? And that does follow.
Yes,
does follow from the word line action and so on.
It gets quite complicated. So you can show, for example, I mean, it's not easy to argue. It's not difficult to argue that if you perform some analytic continuation and your action, the imaginary part of the action always is positive, then it's not possible. Then you just don't cross any branch cuts.
Mm-hmm.
But in general, it's more difficult. I mean, it's not so difficult to prove what types of singularities can appear. And as I mentioned, they could be either logarithmic or square root branch points. But it becomes much more complicated to determine where those branch cuts can actually lie. So the way I do it here is by direct numerical integration.
I see. Okay. Thanks.
And sorry, just continuing on that, if you've got two different branch cuts, it could be that when you go through one, you end up into another and so on. So, the full branch structure, is there any way of exploring that, or is that just way out of reach?
It's way out of reach. So as you can see, I mean, as you can tell, this is basically the simplest Feynman diagram you can write down, and already it's quite complicated. I mean, you can sit down and you can analyze, monodromies and so on. You can do it, but then at some point it just becomes extremely more complicated. And actually, that leads me to my second example.
Thank you.
Sure. So the second example, let's do a very similar diagram, but at 3 loops. Okay. So also you have some external particles and some internal particles, and in principle you can say study just the massless scattering. Okay. So if you just do massless to massless, then what you would find is that the singularity locus, or what in scattering amplitudes literature we call the alphabet of singularities, is very simple. It tells you that either S, T, or U can be 0, and these are the only singularities of this diagram. Okay, so it's very simple. But then what you can ask, what happens when we put masses in our theory? So more generally, when you include masses, this is what comes out of solving Landau equations, or solving the saddle point equations. Okay, what you find is that singularities of this specific Feynman diagram lie on this degree 128 curve in the ST plane. And in fact, that curve is so large that it would be impossible for me to write it on a single slide because, for example, the last component here has 300 plus terms. So basically the point is that those curves become incredibly complicated, and it's very difficult to say anything concretely about monodromies, discontinuity structure, and so on for generic masses. And actually, this type of computations would have been even impossible last year. And this was the reason why we introduced this new package called Landau.jl, which does those computations for you. So in case you have some Feynman diagram and you wanted to find out where the singularities of these Feynman diagrams can lie, then this package could tell you. If you like to think more in pictures, let me just repeat the same diagram that we've seen before, real S and real T. And what happens on this diagram is that each line here, so once again, the shaded region, this is the S channel, T channel, and U channel. And the blue lines are singularities, the anomalous thresholds. Okay, so as you can see, you can zoom in somewhere here, and this becomes much more complicated. And this is essentially the reason why I think it's slightly hopeless to learn anything about monodromies and the monodromy group here. And many, what you can actually show is that many of those curves lie on some unphysical sheets. So all of these in blue lie on unphysical sheets, but there are some pieces of these curves here, the ones in orange, so 5 components, which you can also see here, that lie on the physical sheet. So these are the ones that would actually contribute to physical scattering if you measured it at this point. Okay, is there any question at this stage?
I'm sorry, these are things that would invalidate the kind of dispersion relations we normally use or not?
In those cases, yes, in those cases, we currently do not know of a way of writing dispersion relations in here. Once again, the dispersion relations can be only written down when you have scattering of the lightest states with a mass gap theory, and this is explicitly not that.
But sorry, if you don't mind, let me ask again. Then it seems sort of suggestive that every time is it right that every time you find a place where you cannot write dispersion relations, you're also scattering things that you shouldn't be scattering because they decay? Is that always true?
No, the exception are massless particles. So for massless internal particles, we also don't know how to write down dispersion relations, but they do make sense.
Right. Sorry. So if we stay away from massless particles for a while, if we're only dealing with a massive theory, then is it right that every time you find a case where you have extra singularities on the physical sheet, you're scattering something you shouldn't be scattering?
I would not commit myself to an answer, but it's certainly in this diagram it seems correct.
So it could be that the dispersion relations continue to hold sort of non-perturbatively for every amplitude that is well defined, right?
Modulo massless particles.
Modulo massless particles
might be true. Yes.
Thank you.
Sorry, Sebastian. Why is it in this case that is true? I thought here. So if you go back on the previous sheet, previous slide. No. I mean the 3-loop diagram. Yeah, over here. So here, all these can be light particles, right? The lightest particles, and even then you will find such a structure, or even the big M can be smaller than small m, and even then there will be some complicated structure, right?
Yeah. So what you find? So on this diagram, if you can plug M equals M, for example.
Yeah.
Then you can, okay, so from here you can already see that there's a singularity, this collinear singularity, there's S equals 4m squared and all the permutations and so on. Mm-hmm. And what you would actually find is that these curves move out, and they move out in specifically such a way that there's some region in here where there's no singularities whatsoever. And that region is exactly, this is the real axis. And if you went to complex S-plane, that this region is exactly what allows you to continue between upper half and lower half plane.
And even for the case of, let's say, capital M smaller, right? Even then that will happen.
Yeah, exactly. Capital M smaller than lowercase m, and that you can show. And actually, you can put a bound on how small it has to be. How small it can be. Yes.
Okay. Thank you. Thanks.
Okay. Okay. Any other questions in the meantime? Okay, so luckily for us, for the question of crossing symmetry, we do not need to really understand the full how complicated the S matrix can be. Essentially, the only thing that we need to understand is where singularities cannot appear. So we only need to constrain the places where things are fully analytic, and we do not have to worry about some other places in the kinematic space in which there could be singularities. Okay, so before diving into details, let me mention where we're going. So as pointed out by Witten, the only class of anomalous thresholds that could pose a potential obstruction to crossing symmetry is the following. Okay, so what this diagram is meant to represent is some scattering of m to n particles, and all the lines here are on shell. So this is an example of an anomalous threshold, and the ones that we have to worry about are the ones in which the particles are aligned in two beams, the red and the blue, and in principle they can exchange massless states. Okay, so that's an example of an anomalous threshold. Remember that everyone here is on shell. And the statement is that as long as you can show in your theory that such anomalous thresholds do not exist on the physical sheet, then crossing symmetry is true. Okay, so to understand why this is where we're going to end up, in order to understand why this is the case, we first of all need to understand how to avoid real singularities in the real S and real T, and then we have to understand how to avoid complex singularities. So the real singularities are important to understand because you need to continue within a given physical region. But then ultimately, what you need to do is you need to complexify the kinematics and go to another physical region. And so it's going to require analysis of complex anomalous thresholds. And this is exactly necessary because what we need to do in pictures is we need to rotate the external states from being in the future light cone to the past light cone and vice versa. Okay. So let us come back to this condition that we needed to impose. Remember that the imaginary part of the action being positive was essentially the Feynman I epsilon condition. It turns out that this is actually very simple to impose by simply giving the word lines infinitesimal phases. So you start with some Schwinger parameter alpha, and then all you have to do is you need to give it a small phase in the complex directions, such that the phase is proportional exactly to the derivative of the action, like so. Okay, and epsilon is infinitesimal. So then you can show that the result of doing this is that the action acquires a small non-negative imaginary part, like so. So the action goes into itself plus these corrections. And as you can tell from those corrections, the Schwinger parameters are always positive. And then here we have a square of a real quantity. So that always imposes the correct I epsilon prescription, except exactly at the saddle points. Okay, and it turns out you can essentially apply these conditions, and this deformation of the word lines. What it does is essentially it also deforms branch cuts in the kinematic space. And it does it, moreover, in precisely such a way that you see, each branch cut could have been deformed, for example, in the upper half plane or lower half plane. We know that this guarantees that it's going to land us on the physical sheet defined by the Feynman I epsilon. So it reveals to us exactly the parts of the amplitude where the ones that we are interested in. Okay, so for our purposes, we're interested in this because this guarantees analyticity in some I epsilon neighborhood of the physical region, but by itself, it does not constrain anything about the analyticity away from the physical kinematics. Okay, somewhere in the complex domain.
Sorry, Sebastian, just to understand, so this complexification of your Schwinger parameters, does that change your answer? Because of Cauchy's theorem, it does not change the answer to the
It does not. As long as epsilon is infinitesimal or sufficiently small, then the effect of this is essentially selecting the correct homology cycle for the integration in the Schwinger parameters. And of course, that the choice of the cycle is not unique. It's exactly the the choice of like plus I epsilon or minus I epsilon prescription. But this is exactly the way in which you have to do it in order to have causal propagators.
Great. And then if you make epsilon a little larger, it doesn't change your answer at all.
Well, it has to remain infinitesimal. So as long as the corrections don't, you can put a bound on how large epsilon can be, and as long as the corrections in the epsilon square, epsilon cube don't change the sign, then you're good. The only thing that we care about is that this is positive.
I see. I was thinking that if you just if you're changing this epsilon is like changing a contour in Schwinger parameter integration space, and as long as then arcs at infinity can be ignored, even with a finite deformation, you shouldn't change the answer. Is that wrong?
That's not guaranteed.
That's not immediately clear.
Not guaranteed.
Not
so
yet.
The finite deformation might, in principle, break down at some point.
Because the arc at infinity might contribute.
No, sorry. So the way I think about it is that the original Schwinger parameters are integrated from 0 to infinity, and then this deformation essentially rotates it off the real axis. But what might happen is that there could be some saddle points close to the real axis, and what you want is that this deformation essentially doesn't pass through them.
Thank you. Yeah.
And this guarantees that for infinitesimal epsilon, this does not happen, and it guarantees also that there's some infinitesimal neighborhood of this region here. And this is exactly the perturbative version of the non-perturbative results that was proven more abstractly 60 years ago. Okay. So we're getting there. So now remember what we need to do now is we need to continue in the imaginary directions. Okay, so now what we have to do is we have to do analytic continuation of the external energies as opposed to internal Schwinger parameters within the complexified light cone. Okay, so this can be done at arbitrary multiplicity, but for the purposes of this talk, let me do 4 points. So what I mean to remain within the light cone, I mean that we are not supposed to violate momentum reservation or on-shell conditions. So the specific deformation that I will employ is given by going to the light cone coordinates first. Okay, so I'm going to go to light cone coordinates with the plus and minus directions going along the light cone and some space-like directions. Okay, first of all, I'm going to go to a frame in which within the light cone, the particle 1 is diametrically opposed to that of particle 4. Okay, so in pictures, it goes like this. And likewise, I'm going to impose that the light cone components of P2 are opposed to the P3. Okay, so in this case, 1 and 2 are incoming and 3 and 4 are outgoing. And this is just a trace of a frame. We didn't even fix the full Lorentz, all Lorentz generators. And now what we want to do is we want to deform this kinematics, starting from this kinematics. We want to deform it with the parameter z. Okay, z to begin with is equal to 1. So this guarantees that the energies of particle 2 is positive and that of particle 3 is negative. And then what we want to do is we want to deform in the z upper plane to go to z equals -1. The image of this deformation is going to be shown here. So it's going to simply exchange the future pointing P2 to a past pointing P2. Okay, is there any question about this deformation?
So this would be the analytic continuation from the S channel to, let's say, T channel or U channel.
Yes,
physical.
Yeah, very good. So what this is going to do is going to continue, yeah, exactly from S to U.
Okay.
And let me see, I have it on some slides. Okay, I will give it more explicitly in a couple of slides. Okay, any other questions? This is sort of the most crucial slide, so. Okay, so I think it's clear. Okay, so now we've deformed the external kinematics, and now what we can study is how this deformation acts on the internal momenta as well. So Q sub E was an internal momentum flowing through the edge E with the Lorentz index. Now what we can look at is we can look at the light cone components of these internal momenta. And then simply because everyone was already aligned with P1 or P2, then this QE, this internal momentum can be decomposed in the basis. It can be either proportional. I mean, it can be it's some linear combination of components proportional to P2 and to those of P1. So let me call these coefficients for a specific edge E, F sub E and G sub E. Okay. And then what happens is, as we deform the external momentum with this parameter Z, the internal momentum essentially just changes like so. Now, what we want to do is we want to go on an anomalous threshold. So we need to impose that this this edge goes on shell. As a matter of fact, it actually suffices to look at the imaginary part of this on-shell constraint. And after a bit of algebra, you can show that plugging this into here, you can show that this is actually proportional to F times G. And that needs to be 0. So this leaves us with three possibilities. Either F is equal to 0, G is equal to 0, or F and G at the same time are equal to 0. And if you compare it with this equation, it tells us that the internal momentum has to be either purely aligned in the direction of P2, P3, or purely aligned in terms of the other direction, or perhaps it could have no light cone components, and that means it goes within into the page, so in the spacing directions.
Sorry, here you are assuming the masses of external particles to be 0, or
no? The masses of the external particles don't actually enter here.
Oh,
okay. But they could be positive or 0. Okay.
Sorry, and your light cone directions were chosen completely arbitrarily?
Yes, so we choose we choose some P plus and P minus directions, and they're more or less arbitrary.
Thank you.
Okay, so at this stage, the question, this was the type of anomalous thresholds that I mentioned a couple of slides ago, that basically these are the most interesting ones for us, because these are the ones that can lead to a potential singularity along the path of deformation in Z complex plane. And unfortunately, it's currently unknown whether such anomalous thresholds exist in an arbitrary theory.
sorry, when are you calling the threshold normal, and when are you calling the threshold anomalous?
The anomalous, most of the singularities are anomalous thresholds. The special case in which all of the particles would be aligned in one dimension, that would be called the normal threshold.
Anomalous is in some sense unphysical or unexpected, or what makes them anomalous? Sorry.
Yes, sorry, the name anomalous is just a historical artifact, because it does not mean it corresponds to some anomalies or anything like this. It's just historical name, because at the beginning of the S matrix theory, people did not expect that exists, but it turned out that they exist.
Okay.
Anomalous. Okay. So at this stage, as I mentioned, it's unknown if we can perform this analysis in an arbitrary theory. But what we're going to do in this talk is we're going to specialize to planar scattering amplitudes. For example, we can be in large N QCD. And moreover, we're going to specialize to the case in which we can consider arbitrary multiplicity diagram, but all the external particles have to be consecutive, and likewise all the incoming have to be consecutive, and also likewise all the outgoing have to be consecutive. Okay, so this is one example of a Feynman diagram with some high number of loops that we'll be considering. Okay, and in those cases, it's actually quite easy to argue that such dangerous singularities never appear in this plane. The reason is as follows. So we can consider scattering amplitudes with some planar cyclic ordering 1, 2, 3, 4. So this was, let's say this is 1, 2, sorry. Yeah, 1, 2, 3, 4. And if you remember, the momentum of 4 was aligned oppositely to the one of 1 within the light cone, and likewise 2 and 3. Now, what you can argue is that if you study these saddle point equations, is that the momentum, or Landau equations specifically, is that the momentum of the momentum flow along the edges of this diagram, along the perimeter of this planar diagram, has to only flow in the specific direction. Namely, if we go from here, from the sink to the source, then the momentum has to flow in this way, and this way along the arms. Okay, this is if we just analyze it in how it responds to P1, in which case the coefficient of this in this direction of a given edge somewhere here on the perimeter has to be strictly positive. Okay, and likewise, what you can do is apply the same analysis to the other momentum, P2 going to P3, which remember was the one that was being deformed. You can show that along the perimeter of this diagram, all the components within that are proportional to P2 have to be strictly positive with the orientation of these arrows. Okay. In particular, what this means is that the component G also have to be positive. And what this tells us is that there exist some edges in this diagram, somewhere here, which have F and G both strictly positive. And if you remember, the on-shell condition was always proportional to F times G. And if there exist some edges in which they cannot be go to 0, that means that a singularity just does not appear. And that simple argument, in fact, is strong enough to fully guarantee analyticity when rotating from the past to the future light cone and vice versa.
Sorry, the worry was to have this 0 for all the particles, or even a single particle?
Excuse me, can you repeat the question?
The worry of this anomalous threshold was for a single internal particle, or all the particles?
All the particles, yes.
All the particles, I see.
Yeah. So one thing that maybe I should have done better is that there are anomalous thresholds, and there are also which were the bulk saddle points, but also there's the saddle points when you go to the boundary. And those, when you go to the boundary, corresponds to shrinking some of the propagators. But as long as you shrink as a propagator, you just land on a different Feynman diagram, which is also planar. So all the arguments are given for arbitrary diagram. So that means that we covered all possible saddle points, bulk and the boundary.
So Sebastian, when in the sort of traditional analysis of these Landau singularities, you get potential places where things could go singular, and then you have to check whether those potential places are a pinch or something you could deform away from.
Yeah.
And was it the case that in your situation you could have potential situations where things look problematic, but you never pinch? Is that sort of what's going on here?
Exactly, and I think this is what's going to happen for non-planar diagrams. In here, for planar diagrams, the situation is way easier. It just happens that the pinches don't happen in the first place, so you don't have to deform anything away from it. Or alternatively, you can think about the Z deformation as some kind of way of avoiding something that could have happened otherwise if you did not do this specific deformation.
I see, but you say that for the planar case, it's not even like there's a naive singularity that you have to deform away from. It's just not there.
It's not there, yes.
Okay, thank you.
The only singularity, but okay, I'll come back to one point that I wanted to stress. But okay, so with that, what we know is that we can continue between do this analytic continuation when we avoid the real singularities and complex singularities, and as we explained in 2 steps. Sorry, is there a question? Okay. Sorry, I think, okay. So while going through this diagram in more details would take too much time, so I would refer you to this reference. It can be simply explained in pictures. First of all, we shown how to, with the I epsilon prescription, to basically rotate within a given physical region. This corresponds to changing the momenta of the external particles in such a way that you do not exchange anything from the in to out. Okay, so these are this kind of deformations that allowed us to basically move particles around. In this case, for the sets A and B, where here I decomposed all the incoming states into 2 sets, non-empty sets A and B, and all the outgoing states into non-empty C and D. Okay, so this allowed us to exchange A and B. Okay, then we land on this picture, and then we discuss the deformation with the Z parameter that was going between future and the past. Okay, and what this allowed us to argue for is that the deformation is smooth, namely you don't encounter any singularities when you exchange the particles in the set C into antiparticles in the set C bar, and likewise B into B bar. And then all it takes is just repeating this in a specific order, which you can go through. In the step 3, for example, we exchange these 2 particles, you land on this diagram, then you exchange A and B bar from future to the past, and then in the final state, stage, you also exchange D and A bar. And in the final step of this deformation, you land on a process that we started with, A and B incoming, C and D outgoing. And we ended up with a process in which we have B and C bar, where bar denotes the antiparticle, and incoming, and D and A bar outgoing. So in the special case, at 4-point scattering, this would be S channel, and this would be T channel. So in fact, let me give you a more visual way of understanding this at 4 points once again. So we can look at this S-T plane, and we have this S channel here, U channel, and the T channel. So what happened in the first step is that we traveled within the S channel physical region, and then using some I epsilon deformations, we argued that you can go around the potential singularities and land us on some starting point for the next deformation. Then the step 2 was this complex deformation and with the Z parameter, and then you can show that the image of that is that T remains constant and negative, and S goes in the upper half plane. Using this, we can continue between S channel and the U channel from above in the upper half plane, and then repeating the very similar steps, we land here, then we go, fixed S, we continue in upper half plane T, in T, and then we land on some generic process in here. So this is a path of analytic continuation between arbitrary process in the S channel to an arbitrary process in the T channel. Okay. Any question about this diagram? Okay, if I went a bit too quickly through it, please maybe ask me about details after the talk. Okay, so this in general, this was a 4-point example, but more generally, what it tells us is that we can talk.
After the step 2,
yes.
Are you approaching the U channel from the right direction in the physical direction here, or?
Yes. So let me clarify what right means. In this case, we approach it from the upper half plane in the S plane, and you can show that for the planar amplitudes, this is actually correct prescription, meaning it's consistent with the positive I epsilon, the plus I epsilon. that part is no longer going to be true for non-planar amplitudes.
Even for this thing.
Sorry, I think you muted. Sorry, can you repeat the question?
Yeah, so so in this deformation, S plus particles are on shell and momentum conservation is there. Okay, then S plus T plus U is 4m square.
Yes, that's correct.
So yeah, suppose in the second step, T is real and negative, but S is positive imaginary. So U is 4m square minus S minus T. Now, if S has positive imaginary part, means you have positive negative imaginary part, right?
Yeah.
Then when you approach the U channel after the step 2, you reach at least the diagram you show there in the S plane. It is a red line coming from the real axis to the upper half plane to the real axis. So that means it's not the physical region in the U channel. Am I right?
No.
Because it's the negative U, imaginary U you are approaching, because U is 4m square minus S minus T.
Yes, so you're assuming that approaching U channel from U negative epsilon is not physical, but that turns out to not be the case for planar diagrams. You're absolutely right that it might not be physical for generic process, but it turns out for planar diagrams is actually correct. And the way that you would determine whether it's the correct prescription is you have to track back if it corresponds to plus I epsilon or minus I epsilon.
No, the reason I was actually asking this, suppose you go to, after step 2, you go to the U channel process, which is in the physical region, then you can stop here, right? I mean, you can call U channel to be your T channel, and this is why there is a 3rd, 4th, and 5th. I mean, if it is just what you call T, what you call U, right? So I know that Brosefte and Glaser, they had to go to this process because after step 2 kind of this thing, they reach to the U channel unphysical side, then they have to go to like that, and then they reach to T channel. But if you really, I mean, it is true that for planar diagrams, U channel, you are approaching from the physical region, then you can stop here, because U channel, you can call it T.
Sure.
So that's why I was...
So this is precisely a great question. So this is precisely the reason why you're absolutely right that we could have stopped here, and then without loss of generality, this implies all the other results. The only reason, and for planar amplitudes, this would be correct, but the only reason why I did not want to do it is because I wanted to explore a path of analytic continuation that would be valid more generally, even though in planar diagrams you can do it in a simpler way. And at 4 point, this is actually quite trivial, but the whole difficulty is with doing this at higher multiplicity, which is exactly why I wanted to go through this process in this specific way. So that's a specific case of a more general deformation that exists at arbitrary multiplicity, which is the reason why it looks slightly more complicated than it needs to be.
Okay.
And let me, since you seem to be very much familiar with the work of Brauss and collaborators, let me also mention that Brauss, in principle, had to go first to asymptotically large energies, and analytically continue. And in this case, it's not necessary. So in this case, you can do this continuation at any finite energy.
Yes. Okay.
Great question. Thank you. Any other questions? Okay, let's see if I can finish within 2 hours. So what we've learned is that you can do analytic continuation between the channel AB carrying CD and the other one that we explained in the pictures. So strictly speaking, what this equation means is that every time the left-hand side exists, meaning that the scattering amplitude in this channel exists, then the right-hand side also exists, and it's given by analytic continuation of the left-hand side using the specific path mentioned on the previous slide. That itself is an analytic continuation between crossing channels, but not yet crossing symmetry in the way that I wanted to define it at the very beginning, meaning exchanging a single particle into a single antiparticle. However, what you can do, at least when you have at least 5 particles, is that you can repeat these steps in 3 different ways. Okay, so you can take your particles, originally scattering some sets I and j into KL with some last particle n, and then you can start grouping them in different ways into these sets, and then after 3 steps of doing this, let me not bore you with the details. The upshot is that what you can do is relate this process with an outgoing particle n into this process with an ingoing antiparticle n bar. So at least starting at the endpoint, this is exactly realizing this dream that you can continue a single particle into a single antiparticle without encountering any singularities. So this is in fact the first realizations of crossing symmetry in the sense of continuing a single particle into a single particle in the specific case of planar scattering amplitudes, and it's going to be valid at every order in perturbation theory with any masses, spins, and multiplicities. So the masses, spins, multiplicities never, multiplicity matter, but the masses and spins actually never appear in the analysis. Okay, and as I said before, this is strictly speaking valid at least 5 point scattering for processes with consecutive in and out states, and only in CPT invariant theories. Okay, and I think this is going to be my last slide. So let me briefly summarize what we've learned today. We've asked this age-old question about the S matrix and whether the one with a particle and the other with an outgoing antiparticle can be related by analytic continuation. First of all, what I've done is I've outlined some of the difficulties with the previous non-perturbative approaches in proving the statement. Then what we've introduced is a new way of thinking about analyticity or singularities of the S matrix as wordline saddle points and precise way in which we can try to avoid them. Then we've identified the types of singularities that could pose a potential obstruction to crossing symmetry. And finally, what we've done is we've shown that the crossing holds for any planar amplitudes up to the caveats that I mentioned on the previous slide. So with that, let me thank you for your attention and ask for any other questions.
Thank you very much, Sebastian, for a wonderful talk. Let's all unmute and clap. Okay, so we have had many questions during the talk, but I'm sure there are going to be a few more. So if Sebastian, you don't mind staying up for a few more minutes. Okay.
Sebastian, maybe I can ask you, so, right at the beginning of your talk, you said that your work will not imply that S matrices and matter-Chern-Simons theories are crossing invariant. And can you sort of say what stage of, in your proof,
Yeah, thank you. That's a very good question. So let's say we're talking about large N only. So what we've shown is that at least for planar Feynman diagrams, you can always continue, say between S and T channel or whatever. This does not yet imply that the function that we got after the analytic continuation is the same function that we expected to find in the T channel. In order to guarantee that, we also needed to know that the Feynman rules are crossing invariant, meaning that we get the same function. And that does not happen in Chern-Simons theories. So what happens in Chern-Simons theories is that it's still true that you can analytically continue along the path of deformation that we discussed between different channels. But then at the end of the computation, we know that the result is not yet what we want. We have to multiply it by some additional phases and do all the things that we would have to do at tree level anyway. So the additional thing that we bought ourselves with this progress is that now we know that about the absence of singularities in the sort of upper planes.
Thank you.
Thank you.
So Sebastian, one question. So here on this particular slide, you talk about how the having Mendel-Stam invariants not independent of each other could potentially be problematic for higher ends, even in D=4. But that issue never arises, right, in your planar diagram analysis. The planar diagram is still, isn't that the case?
That's correct. At the maybe let me point you to the place where why this didn't matter. It didn't matter essentially because, well, actually it's not on those slides, but you can devise a similar analytic continuation at arbitrary multiplicity. And it's always the analytic deformation in terms of the four momenta. And as long as you do that, then it implies that you always, you're not constrained by the space-time dimension. Whereas if we wanted to do analytic continuation at the level of kinematic invariance, then we have to worry about additional constraints that appear on the level of kinematic invariance at multiplicity 6 and higher.
So how do you, yeah, sorry.
Maybe I can also comment about two dimensions, because that's also special. Here, strictly speaking, what we needed to assume, although I didn't have time to explain it in the talk, is that these coefficients are also the space-like coefficients are sort of generic, and that's essentially what breaks down in two dimensions. That we do not have the special freedom of the space-like components, and this is effectively, if you track down why this would break down into dimensions for integrable theories, it's this. I see.
But even so even this not the particle going to antiparticle, which should break down in 2D theories, but even this rotation will break down in 2D theories. Even this the first step would break down. I thought that would be okay, right?
No, the what specifically this first step is going to break down, not the second.
I see. But that the first step is in the same region, right? So you don't have to analytically continue or anything. Even then it will break down.
I would have to think more about this first step. I think there was a good there was a good answer to this question, but maybe now it's too late in the night to recall it. But the point is, 2D is to the kinematics is too degenerate to study this question.
Okay, thanks.
So one more sort of general question, Sebastian. It's very vague, but anyway. You talked you mentioned in your talk that the analytic structure, the branch structure of these correlation functions, if you go off the principal sheet, for instance, is completely untamed. It's very, very difficult to understand. There's a sort of similar question one could ask in conformal field theories for the full branch structure of the correlation functions in conformal field theories. And I'm not sure that's completely understood either, but it seems under better control, perhaps. So I was wondering whether one could learn something about the branch structure of S matrices by embedding them within conformal field theories and defining them as, from there.
Yes, so there's been recent progress on this. So I think the work that most directly points to the answer of your question would be the one by Komatsu and I think Bolt van Ries and one other person, in which they studied exactly the question of analyticity. And exactly the question of how the anomalous threshold, the triangle, appears when you take the, I think in this case, I forgot which specific way of taking the flat space limit they took, but it was starting from ADS and I think going to limit of heavy operators. And in that limit, they were able to constrain the analyticity structure. And essentially, the reason why I'm a bit unsure about this way is that essentially their analysis was coming up with an analog of Landau equations, but in ADS. And those were much more difficult to solve than the flat space analog. So it seems like, at least the way that they were doing things, we're not making the question simpler, just becomes technically slightly more complicated. However, there's also a beautiful set of works of many people, Simon, Caron-Huot, Vratati, Dalman-Mazak, and collaborators, in which they also appearing in your work from April, in which you constrain the high energy behavior. So you can say something about the large, in this language, fixed T large S behavior of scattering amplitudes, even though these are usually, maybe like large N statements and so on. I think it's a good direction. So one of the questions would be if we can generalize those to higher multiplicity as well.
Just a question that what do you mean to Siraj that by embedding this S matrix in conformal filter, is it the flat space limits of ADS? That's what you mean? Or?
Yeah, either flat space limit or some sort of bulk point limit.
Okay. But there is recently this celestial amplitude thing where directly we map, they map this S matrix to safety correlators. Maybe they are these questions addressing, because in CFT, 2D safety, we have better handle to the singularities. So maybe...
the reason why Shiraz was pointing in this direction was that in CFT, in ADS CFT, we have some control over the convergence or superconvergence properties of the CFT correlators. So then we can try to translate them to the flat space S matrix in the limit.
Right.
In the case of the celestial CFT, that theory is not as well developed to say anything about the correlators on the sphere, which is not implied by sort of going the other direction.
I see.
So isn't this some weird, some CFT with weird rules, which are not very well understood, or has it been mapped to a conventional CFT? I'm not aware.
It's not a conventional CFT, so we don't know if the conventional CFT. Well, for sure, the conventional CFT2 results would not translate. They're more exotic. CFT, which is not very well understood. And what I was pointing out that in this case, the only direction in which we can hope to understand more about the CFT is specifically starting with plane wave scattering and then translating it into this other basis. But we wanted to go the other direction.
I have just one more question. If you...
Maybe we can finish first with. Shiraz, did you have?
I have just one quick follow-up. This question of the detailed Brown structure of conformal field theory correlators. Do you know how well they are understood in general? Meaning,
sorry, was the question about CFT or
just CFTs? Yes, ordinary CFTs. So you go through one branch, you come out through another. When do you make a loop? That kind of thing.
Okay, I don't. Maybe I'm not very qualified to answer this question, but
thank you. Yeah.
As far as I understand, the types of statements that we there's also, of course, a lot of progress recently in formulating formulating analytic properties of the for example, convergence of the OPEs starting from these Whiteman-like axioms of CFT, like Rishkov is doing with Kravchuk and so on. But I think these statements are mostly talking about things like convergence of the OPEs, say, or studying the radius of convergence of the OPEs. In my opinion, this is roughly speaking what people have pursued in the past in the QFT language, also essentially redoing what the Gross, Epstein, and Glasser did for the S matrix. So I think it's the similar type of analysis on both sides, on the CFT sides, or doing directly QFT S matrix. So also from that perspective, it's not clear if, but we've just commented on the fact that the QFT side was difficult to generalize to higher multiplicity. It was difficult to generalize to massless particles. It's not. I'm not familiar well enough with the topic to answer whether those questions specifically would be easier to understand in CFT, but it might. It would be actually quite exciting.
Yeah, I'll just ask one more question, maybe more generally to the audience, maybe Abhijit. The kind of question I had in mind is that if you think of this, the space of 2D CFT correlators as a two complex dimensional manifold, what is the topology of that manifold when you go through all of those? What is that? Is that a theory dependent question? Is there a general answer?
Well, I think, yeah.
CFT correlators are supposed to be single valued. So in general, in principle, they don't have.
I have some answer to Siraj's question. I mean, about this thing. So basically for unitary theory, we know that for conformal blocks, the singularity lies on the cross ratio space, lies on 0, 1, and infinity. And there is a map from the cross ratio space to the upper half plane where this branch structure can be completely unwrapped. That was by Jamolachiko. Because I know this because I worked in a problem where we employ this upper half plane and so some where this single valuedness implies some gamma 2 invariance, some subgroup of PSL2G on the upper half plane, and that is there. But as long as unitary CFT 2D CFTs are concerned, it is believe that all the singularity lies above 0, 1, and infinity, and the branch structure can be completely unwrapped in the upper half plane by a map.
But let's suppose that we know that these branch points are 0, 1, and infinity. Now, as you circle through various branch cuts, it could be that you circle 5 times around one branch cut and 1 time around another, and then you'll end up in the same place as going 3 times around another.
Yes.
There could be a complicated topology in the space of the manifold on which these correlation functions are defined.
Yes, that depends on what primaries run in the intermediate channel, because the powers of, because it is always some factor of x, z1 minus z2, or x minus 1 times some h conformal dimensions. So depending on conformal dimensions, how many times we have to go around 0 and 1, that can be
and you're talking about 2D CFTs or more generally?
2D CFT. Our work is on WGW models.
Okay, yeah, thank you.
But sorry, was this comment about conformal blocks or correlation functions?
Correlation functions are, of course, monodromy invariant, means single valued. So out of once we know the branch structure of the conformal block, then we ask what is out of this, what is the crossing symmetric or the single valued object. So
single valued in Euclidean space. But once you go into Lorentzian space,
okay,
correlation functions are also multiple. There's monodromies, right? I mean, and that is the interesting, in my opinion, the interesting question.
Yeah.
I see.
Sorry, can I say something?
Please.
So I think the monodromies, as he pointed out correctly, the singularities at those places. But if you think of these monodromy group as being generated as a monodromy, which is around 0, and a B monodromy, which is around 1, then the monodromy around infinity would be A times B. So let's not count that as a separate one. Then I believe that the monodromy group is a free group
in 2 elements. Yeah, into
And
elements.
what is the argument for that, Abhijit?
Well, no argument, but this, generically that would be the case, but
and what about interference between the monodromies in Z and monodromies in Z bar? Are those completely on their own? Well, they're not completely on their own because there's Euclidean single valuedness. There's some connection.
Yeah, there's Euclidean single valuedness. That's right. Yeah.
So we know that if we do something in Z and the opposite thing in Z bar,
opposite thing in Z bar. Yeah.
Like
but
nothing.
if you just, let's say, do things on Z, then it would be free. I think there will not be any relations. But I think it would be nice to.
Yeah, you think it would be nice?
Think about it more. Yeah.
Okay.
And also I think, if you ask, I do this, I do that, I do, all sorts of crazy things in Z bar, and you ask yourself, does it correspond to some sort of a correlator on the Lorentzian cylinder?
Yeah.
But I think the answer to that is also probably no.
The answer is no.
I think Lorentzian cylinder maps to a particular slice of this. That's what I believe, but it would be nice to. So this is something that I want to think about. I thought a little bit about it, but not much.
But it should be that every one of these branches has some physical interpretation. Right?
I would like to say, yeah, it would be nice to have such a thing. I agree. But it seems that the freedom that you have in monodromies
is too much.
It's too much.
Yeah.
Than just having
because it's exponential, right? It grows exponentially.
If it is a free group.
Yeah.
So if the other thing is actually true, then there would have to be relation, as you are saying somehow.
Yeah.
Yeah.
Okay. Thank you.
And one more question. Sorry, kind of along these lines. So why do you think that So with Sebastian, isn't it true that in order for you to show the crossing symmetry, you did not quite use the fact that the correlation functions are somehow in position space permutation invariant, and then you did not go from there. So Shiraz's point of view of having to understand this CFT. To understand the branch structure of the CFT position space correlators, and from there perhaps go into understanding some sort of a crossing symmetry property of, let's say, bulk S matrices, let's say in the flat space limit. How it's not quite the same kind of thing, right? I mean, even before that, you would rather use the permutation property of the position space correlators in the ADS, let's say, in the quantum field theory itself, right? Before going to the boundary analog of that, or is there a different point of view that somehow thinking about it from the CFT point of view buys you more? So I don't know whether I phrased the question well, but
yeah. I mean, there's a couple of questions. First of all, there's crossing symmetry for the boundary correlators themselves. This is not directly the same as bulk crossing symmetry. In order to prove the bulk crossing symmetry, or the thing that I was talking about today, you really have to connect the future and the past. I'm not really sure about those questions, although I'm sure these would be fruitful approaches. I should say that I think crossing symmetry is a problem that not many people think about, but I find it an important problem. So whatever. I welcome any ideas of whatever you think might be useful approach coming from ADS or some other approach.
So before we end, can I make a small comment? Just sorry, Sebastian. It is just related to my previous comment about Shiraz's question about this thing. So another way to see that you may not be that any monodromy kind of thing will give you some configuration on Lorentzian cylinder is because you fix the time ordering, right? Usually you fix the time ordering. So when you go around something, okay, it fixes the direction of going around. So if you go around clockwise and then you go around B and then you go around anti-clockwise, that is something you cannot achieve by a particular time ordering, because time ordering would fix the direction of going around, let's say Z or Z equal to 0.
Sorry, did you mean time ordering or ordering? I don't necessarily
ordering. I meant ordering. Sorry, ordering, not time ordering. I meant ordering.
Yeah. No, but I completely agree with you. If it has exponential growth, then 16 different multiplying something by 16 doesn't help.
Yeah.
Yeah.
Okay. Yeah. So, sorry, Sebastian. Now let's take a few more questions. If there are any for Sebastian, we already have many questions. So Sebastian, I'm sure is very tired also. So.
Yeah, can I ask one last question?
Okay, last question. Let's have last question.
So you have shown one integral where first this worldsheet action was defined. Can you show that?
Yes. This one?
there are some integral maybe before that.
That one?
Okay. So yeah, so just a comment and then question that so for Feynman diagrams, you in showing your parameterization, you can go to that. I think for non-local theories like super string field theory, you will have a similar kind of starting point, except the n will be some different polynomial, the numerator of, and all of your, okay, I read your paper a few months back when it came to archive, but okay, I forgot the details, but I believe that same thing holds, all the comments mostly hold for non-local theories also. And advantage is that in string field theory, here each Feynman diagram has this UV divergences, right, after some dimension, but there always it is UV finite. So it is more concrete in a sense that crossing symmetry. So at Feynman diagram level for planar diagram, so ultimately planar diagram helps us to have a direction in the arrow, right? You showed in the external outermost edges there is an arrow, and that helps you to conclude that singularities will not occur there for this deformation. So I think that will also be true for string field theory. So question is that you at some point said that at some point we need to understand what is the difference between locality and causality. I understand that all the old results where primitive analyticity was proven and then the analytic continuation and crossing symmetry was proven was from micro-causality and locality. That's why people used to believe that those are the locality or causality, those encodes this. But after this Delacroix, Erwin and Sainz work, that even for at Feynman diagrammatics level, non-local theories also have same analyticity and crossing symmetry. But I do not know, I mean, how to approach these. You said that locality has to be, different from causality. How can one approach these? Do you have any comment?
So precisely the work of Sen and collaborators is precisely realizing this in the special cases of 4-point scattering, that you can essentially disentangle the assumption. So basically their work implies that after you specialize to perturbation theory, the assumption of locality was not necessary, because they proven that all the Feynman diagrams that they come from string field theory or any non-local QFT, at least at finite loop level, have to be analytic in the same domain of analyticity that Bross and collaborators did.
Yeah.
If you wanted to go beyond, of course, that suffers from the inconvenience of the fact that, for example, it does not capture massless particles. So if you wanted to include those, and for example, if you wanted to go along the same path or similar path to what I was what I was describing today, then you would indeed have to analyze the version of this.
Yes, their derivation, of course, requires that intermediate channel massless particle cannot propagate. But suppose we take a SFT Feynman diagram, but we do not compute off cell. I follow everything you followed from this step on cell. Same Landau equation will come, because there is, I forgot the authors, there is a paper that same Landau equations will be there for non-local field theories also. So everything follows from here. And for planar diagram, see, can you go to that diagram, ST plane and U channel? I was discussing at some point, so that diagram, yeah.
Yeah, so you would have to go to this reference, which I believe is Dombulis and collaborators.
Yes, right.
And see if all the steps carry over. I have not done that, and this is a subtle subject, so you have to be sure that all the epsilons are in the correct places, and all the
Okay.
It's not enough to just know that the Landau equations are the same. You also have to be careful with this sort of positivity constraints and so on. As long as you can check that these are in the place, then everything would also generalize to non-local theories.
Okay.
Okay, thank you very much, Sebastian, for again for a wonderful talk and very clear talk. and answering all questions very patiently. Thanks a lot.
It was a beautiful talk, Sebastian, and so so explicit and so unhidden. Everything was great. Thank you so much.
Thank you so much. Great questions.
Bye. Good night.
Bye.